It's something they need to consider. So,
but again, Mega they do kind of champion earth testing, don't they? Electrodes.
Yes. Somebody just mentioned that. I couldn't get the name actually. My Mega's all right if you're chatting about the test from this morning. We are indeed chatting about the test from this morning.
Hi, Scott. We're carrying on.
Yeah. Welcome to our life. We are really boring, I tell you.
Yeah, we are.
Right. Yeah, Scott, it's the bane of our lives, isn't it? Yeah. We start talking electrics, that's it. The wife just sort of disowns us.
Oh, I was kicked out into the garage, wasn't I?
Yeah, you were indeed.
Yeah.
I've been kicked out into a cabin in the garden, so I generally live in my shed. Yeah, it's a sad way of life, but there you go. Oh, it keeps me happy. It's about all I'm up to nowadays.
I need to put these testers down. Right, before I drop them. Right. Well, welcome everyone. I haven't actually looked at the chat yet. I don't even know if I got the chat up. Yes, I do. Oh God. Okay. Michael, hello. OGS, Andrew, Richard. Hi, Guy, Rich, Chris, John, Richard. Awesome. All right. Is your presentation working? Yeah.
Yes, I've just flicked it backwards and forwards a few times, and it seems to be doing its trick. So, Yep, fine. No worries.
Oh, Montini in here again. Peter, we're going to have to kind of do something together, buddy, with because we've got two great trainers in the chat all the time, and we need to kind of just do stuff. Speaking of which, by the way, I did a course yesterday. We were talking about calculated risk levels for the SPDs. And David mentioned that you did a good article or something on that. So we need to kind of do something on can include beer. Yeah, I've got some. If you've got some of your own, we'll do one. We'll do one later in the day or whatever. Well, it's early enough now, actually. Yeah.
Electronic beer. Yeah.
I'll send you a message later on. We'll do something. We'll sort something out because it'd be good. It'd be good to kind of do some more of this stuff. All right. Indeed. So, this webinar is covering maximum demand and diversity. Now, if you attended the previous, it's the same presentation. It's the same information. Obviously, a lot of people didn't get to that one, so we're repeating this. We're giving these webinars basically a life of 2 visits. And then we're going to try to bring some new things through, and then we may come back and do another wave if there's enough people who still need some level, or if they've just heard about the webinars and they want to come back to them. But again, after these 2 goes, they're going to pop up on YouTube anyway, so they're there and available on demand.
Somebody can only see me. You lucky thing.
Lucky devil.
Paul.
I don't know. I don't know if there's a button you can press to an ugly button, and then I'll appear. Or go between the galleries or something, mate. I don't know. Majority of you guys, can you see both of us?
Yep, there are some buttons on the actual thumbnail videos that you can press different ones, and it will show you different things.
And don't worry, you're not going to close this thing down. I did a test webinar yesterday, and it took me about 20 minutes to learn how to shut the blooming thing down because it plays behind the background. So try the buttons and see if you can click the cameras. Maybe you'll change our orientation, and it will both appear for you.
Dean can only see you. Dean, you are the luckiest person in this webinar. That's all I can say. If you can only see David and you can't see my ugly mug, you've got the best of it, mate.
I'll be doing a lot of talking, Dean, but without my lips moving.
Yeah. Try the little buttons on the top of just above our faces in those little boxes. Try the little buttons there. Flick around with those a few times.
Yeah, it depends on if you're watching on a mobile device. Also, just play with it. And if you struggle, this is all being recorded. And
as long as you can see the presentation and hear the voices, that's all you need. Seeing us is a bonus. No, not really.
Not really. No.
Bit jaded and fudgy around the edges, but there you go. Right, should we crack on?
Crack on. I've got a couple of messages that I'm gonna mute, but I'm here in spirit.
Okay, yeah. I'm gonna try again to hit 45 minutes this time. Try and restrict it to 45 minutes, and then half an hour or so of chat. So we'll see how we go. Right, maximum demand and diversity, clearing the fog. Right. Yeah, this is one, as David said, we did this the other week. Maximum demand. Maximum demand is very, very important because if we don't get this right, then how do we know if the electrical installation that we've got is actually adequate for use? Do we know the supply is big enough for all the loads that are required? If it isn't, then we're going to have a situation where the supply is going to be constantly under stress. That can result in the service head disintegrating, almost, or melting, fires and all sorts of issues. So we need to make sure that we have the maximum demand correct, or at least as correct as we can get it. How do we normally gauge maximum demand, and how do we normally apply diversity? And different people do this in a number of ways, and the trouble is that there's different advice in different books that you go to. If you go to the on-site guide, there are a few tables and not much else. If you go to guidance note 3, there's very little information in there. If you go to the design guide, the IET design guide, there are worked examples. There's various other books and publications out there. NAPIT have got a guide for electrical installations. They do some examples in there. I'm sure the NIC will do the same. The ECA, again, I'm sure they give information on this. But all the advice is slightly different, and it's confusing. It's confusing because obviously guys would like to be doing it the same way. And we always say if we put 10 electricians in a room and ask a question, you normally get at least 12 different answers because we all have different interpretations of things. So what if we get it wrong? Well, if we get it wrong, then the possibility is we're going to lose the supply. If the supply is overrated, the service fuse may just go pop, and then the customer is left in the dark. So they're not going to be too happy about that. And this is one of the issues we have when you get called up and somebody says, oh, can you put a supply in for a new 10 kilowatt shower, and I want a hot tub out in the garden. Can you stick a supply up there? And we've changed our cooker to one of these new big range cookers, 16 kilowatt or more. Can you put the supplies in for us? And first of all, you're thinking, oh, great, a bit of work. This will keep me going for a day or so. And then you're thinking, actually, no, the supply isn't big enough. You say to the customer, well, sorry, you can't have it because your supply isn't big enough. And then you've got the risk of the fact that the customer might say, well, okay, fair enough, I'll go elsewhere. I'll ask an electrician who will do it. And there are plenty of people out there who might actually not be electricians, but they'll do the work anyway. And this is one of the issues, that we're always trying to keep the customer happy and try to get the work, but at the same time, we've got to give the customer the right information, even if it's not what they want to hear. Here we can see there from that service head, that one's starting to melt. There's a bit of the old bitumen sort of leaking out at the top of the cable there. I believe the bitumen was used to seal the cable, and if the service cable gets too hot, overheats, then it will start to leak out. We end up with this black sticky mess coming down the side of the cable. In serious conditions, this can actually catch fire eventually. And this is, again, one of those situations that we don't really want to have. It's not good for business. One of the problems we've got with service fuses, or any type of fuse, is the fact that they can be overloaded on a constant basis. They can run permanently overloaded. 100 amp fuse is not going to trip at 101 amps. An 80 amp fuse isn't going to trip at 81 amps. Okay, and if we look at the Appendix 3 time current curves, we can see that for an 80 amp BS883, or the old BS1361 service fuse, it requires 140 amps to flow before it will operate. Even then, at 140 amps, it will take about 7,000 seconds. Yeah, that's a long time, almost 2 hours. That's long enough to cook a Sunday dinner. So you can have a situation where somebody's installation is actually permanently overloaded, even when on a Sunday they're cooking their dinner and they've got all the oven on and all the rings on for 2 hours. Even then, it may not take out the service fuse. And we think everything's all right because it's all been working. That's not a problem. Even when the current rises to 200 amps, okay, remember this is an 80 amp fuse protecting a cable incoming, yeah, to provide an 80 amp supply. Even at 200 amps, it can take 300 seconds, which is 5 minutes. That's more than enough time for me to have a shower. So you could have a situation where these things are permanently overloaded. You've got the cooker on a Sunday, and even then, right? Somebody goes and has a shower, and as long as they're not in there for more than 5 minutes, the service fuse will maintain itself. They come out of the shower goes off, they go back down to 140 amps. It's still now going to take 2 hours. They finish the cooking, everything goes off again, goes back to normal use. And they've had that period of time where they've had really excessive overload current, and still the service fuse has not popped out. And we could be doing that every week. We could be doing that several times a week. So it's a situation that is common. Yeah. If we get it really wrong, this happens. Yeah. And this is obviously a situation where it's got so hot in the end that it's given up the ghost, and we've actually had a fire happen. Remember that more people are injured or killed by fires than are killed by electric shock. And it's something we've got to remember about electrical systems. You know, forget electric shock. About 26 people a year die from electric shock. There's a lot of people get injured. About 375,000 a year get electric shock and end up injured and needing hospital treatment. Okay, but there's more people dying from fires caused by electrical equipment than there is dying from electric shock directly. And it's something we need to really raise the profile of, the risk of fire from electrical installations. So providing all the correct information on the EIC, the electrical inspection certificate, is very important. If the customer requests any additional works at some time in the future, the additional load needs to be factored in. So if we've got the initial maximum demand calculation correct, then subsequently we go back in and they ask for an additional load. We can then apply the right factors, apply the right amount of diversity, and we can assess with some sort of modicum of accuracy what the new maximum demand is going to be. The trouble is that people have different ways of filling in maximum demand on a test sheet. Okay, and where is it explained? Well, many of us will look at the on-site guide. The on-site guide has 2 tables in there. It doesn't have any other information. It's just got 2 tables. If we look inside the on-site guide, we've got table A1, which is the table that allows us to assess the current demand of a piece of equipment or a circuit. And then table A2, which is the diversity to be applied for an installation, a group of circuits. And that's all it says. It doesn't actually tell us how to apply them. It doesn't tell us how to put those 2 things together. Right, so commonly what tends to happen is that we assess the current demand for the actual equipment on each circuit. We then apply the appropriate allowance for the diversity of the circuits, and then we add the resultant current demands together. And this gives us our maximum demand. And is this the correct way of doing it? Well, this is the way that some places will teach. Yeah, do it circuit by circuit, apply your maximum demand from the tables, add the circuit currents together. There's your maximum demand for the installation. That's how it is taught in a number of places. You know, I've listened to people teaching it that way, but is it correct? When we're looking at diversity, for instance, are we taking account of the type of equipment? Here on the left, we've got a chart, which is sort of a diagram which shows different appliances in a kitchen. The orange one is a washing machine. Okay, the purple one, I call it, no, it's not purple, it's pink, isn't it? Depends on your eyesight, is a tumble dryer. Okay, the washing machine has an interesting cycle. When it first fills up, it fills up with cold water, so it's got the heater working and the motor running, so it's got its maximum load. So for the first part of the washing cycle, it's at maximum load, so generally about 13 amps. Then once the water is up to temperature, it then goes on to the wash cycle, so the heater goes off and it's reduced to just the actual washing load. Then we have a spin, okay, and then we have a bit more load because the motor's running faster, and then it goes back to a rinse cycle, and then it spins again. So the actual current demand changes through the cycle of the actual washing program. For the tumble dryer, it's pretty much full on all the way through. It's on and it stays on. So there's very little diversity within that current demand for a tumble dryer. So depending on the type of equipment, the load will react differently. And the diversity should be applied differently. The other graph shows the likely loading for numbers of people in an installation. So if you've got one person in installation, you can see the bottom line there, the dark line, is fairly low compared with an installation with 5 persons, the top orange line. And again, even within those, we can see differences through the day. In the early morning, a very light load. Then everybody gets up, has their breakfast, so the toaster goes on, the kettle goes on. Yeah. Then people clear off to work, will go off to their daily duties, whatever they're doing, and the load decreases again. And then about tea time, the load increases again, right? As the dinner goes on and kettles go on and all sorts of things, showers go on, and then the load gradually decreases through the night, till about midnight, where it sort of gets down back to its lowest level again. So the actual current demand through the day alters for each installation. Some people talk about number of socket outlets, and the likely load. So if we've got a socket outlet, we can plug something in there. So surely the number of socket outlets would make a difference. Well, here's an installation which has got a number, quite a few socket outlets, but would that use any more than a house with a normal amount of socket outlets? Because surely it's down to the numbers of bits of equipment that people have got, rather than how many outlets they've got. The outlets may only be there for flexibility. They can move a piece of equipment from one room to another. Okay, just because you've got 100 socket outlets doesn't mean you're going to go and buy 100 TVs. You're going to have a TV in a position and it's going to stay there. If you've got a vacuum cleaner, you're not going to have one for each room. You're going to move the vacuum cleaner around the building. So numbers of socket outlets doesn't really indicate the likely load. Another thing that's in the on-site guide is that a board electrician's isolation special. I reckon probably somebody's had a bit of a game there, haven't they, with that installation. Another thing from the on-site guide is it mentions that we should allow 100 watt per lamp for light fittings. Well, when was the last time we put a 100 watt lamp in? A lot of people nowadays are using excuse me, using compact fluorescents. We went through that, and now we're using LEDs. So what was a 100 watt lamp is maybe now a 9 watt lamp. Or what was a 60 watt lamp is maybe now a 50 watt LED. A 5 watt LED. So with the use of LEDs, this business of 100 watt per lamp really goes out the window. So it's about time the on-site guide maybe got on board with that. As I say, they banned the use of, or banned the production of 100 watt lamps some time ago, and yet we're still using it. The other thing is that on the tables, it quite often goes by number of circuits. So if you've got a number of ring final circuits with 13 amp sockets on there, the more circuits you've got, the more load you've got to allow for. Now, again, this is the case of, well, if you've got 2 circuits in a house, a 3-bedroom semi, are you going to have any more equipment in that 3-bedroom semi than a 3-bedroom semi with 4 circuits? Now, surely it's not going to make any difference. It's the same amount of piece of equipment. The fact that you've got 4 circuits in one house and 2 circuits in another isn't going to put any excess demand on there. So again, looking at number of circuits isn't always a true reflection of the demand. What could be, or what is a true reflection of demand, is the number of occupants. If you've got a single person living alone, generally they will require less loading than 4 or 5 people. And we saw that from the graph previously. A single person uses less overall than a family of 4 or 5 living in a dwelling. But again, there will be times when that single person may go into a shower, 10.5 kilowatts, may put the oven on. So again, there's peaks and troughs in the demand there. What about the types of equipment? Well, yeah, hot tubs, swimming pools. Nowadays, people have these inflatable hot tubs, inflatable swimming pools. So, you know, they have heaters, they have pump systems on there. If you go into a kitchen, you may have a kitchen which has got loads and loads of equipment in there. So perhaps if it's got a number of circuits in there, if it's got multiple ovens, dishwasher, washing machine, tumble dryer, various other bits and pieces, we've got to look at that and think, well, hang on, there could be a substantial load here. What about the use of the building? We've got a picture here of a house, but it's not a house. It's actually a shop. It's not a shop. It's actually an Indian takeaway. If you can see if you can see it close up, it's actually an Indian takeaway come sweet shop with a residential accommodation over the top. Okay, so we've got to look at the use of the building as well as the number of occupants. Yeah. Here we've got a family. Okay, it's a family house. Well, actually, they've got 13 kids here. I think they might use a bit more than if you're living alone. So if we look a bit further at Appendix A in the on-site guide, it does say the information and the values given are intended only for guidance. It is impossible to specify the appropriate allowances for diversity for every type of installation. Okay, so basically, it's impossible to give you correct values or accurate values for diversity. It's just a guideline. It's just guidance. Yeah, you've got to make those decisions for yourself. Well, that's a little bit spooky. It continues, the values given in table A2 of diversity, therefore, may be adjusted, increased or decreased as decided by the designer. So whoever's designing the installation, they need to think about what the customer is going to be using, how they're going to use the installation, what it's going to be used for. They need to consider what equipment might be in the building, and they need to allow for that in their design when they calculate the maximum demand and allow for diversity. And that's great, yeah, but obviously the designer might not always know what the customer is going to put in once the customer's moved in. The on-site guide says that the current demand of a final circuit is determined by adding the current demands of all the pieces of equipment. Yeah, and where appropriate, making an allowance for diversity. And the typical currents and additions are given in table A1. All right, so the one that we quite often look at is the cooker. So remember the cooker, we take the first 10 amps of the current demand of the cooker and then 30% of the rest. And if it's got a socket outlet on the cooker plate, we add another 5 amps on there. Okay, so if we take here a cooker, it's a 14 kilowatt cooker. So it takes a total of 60 amps. From the on-site guide, take the first 10 amps, okay, and then 30% of the rest. So 30% of 50 is 15. Add the 10 and the 15 together. So we're assuming 25 amps after allowing for diversity for that piece of equipment. The current demand of an installation consisting of a number of final circuits may be assessed by allowing for the diversity given in table A2, which are applied to the current demand of all the equipment. But then it says the current demand of the installation should not be assessed by adding the current demands of individual final circuits. So it seems that the initial approach that we saw was wrong. We don't do the circuits and then add them together. That is the wrong way of doing it. So that's a big no for that. Okay. So how do we do it then? If that's wrong, how do we do it? Also in the on-site guide, it mentions that the current demand for any final circuit, which is a standard circuit arrangement complying with Appendix H, here we go, is the rated current of the overcurrent protected device of that circuit. And A lot of people read that and think, oh yeah, well that's final circuit, that's a ring, so that's why we use 32 amp for a ring. You know, rather than worrying about what equipment it might be plugged in or not plugged in, we take the current rating of the device. Okay, well, all right, that's fine. But if we refer to Appendix H, okay, included in Appendix H are, yes, standard ring circuits and standard radial circuits of socket outlets. Great, that's what we're doing then. But also includes 16 amp outlets, cooker circuits, water and space heating circuits, and lighting. They're all in Appendix H. In other words, pretty much everything that's in a domestic installation. Yeah? So when we look at applying that rule from the on-site guide about Appendix H, yeah, it pretty much covers all circuits in a domestic installation, a small shop or a business premise. And there we have a domestic installation there. Not really what I would consider to be a domestic installation, but it is. It's a house. Okay, it's not a 2-bed flat or a 3 up, 3 down, but it's still a domestic installation. So even now, again, we need to interpret and we need to apply some sort of engineering view on installations. What constitutes a domestic installation as suggested by the on-site guide? So when we follow again this process, using table A2, looking at the standard arrangements for final circuits, we take the maximum demand after allowing for diversity by taking 100% of the largest circuit and then 40% of the other circuits. That's what it said. That's what it told us to do. So if we take a domestic circuit or domestic dwelling, it's got a 40 amp cooker circuit, it's got two 32 amp rings, it's got a 16 amp immersion, it's got two 6 amp lighting circuits. So by following what was just said in the on-site guide, we would take the first circuit, 40 amp, 100% of that, and then 40% of everything else. So we've got 32 and 32 and 16 and 6 and 6, add those together, take 40% of that, add it onto 40, and we come up with a final maximum demand figure, allowing for diversity, of 76.8 amps. Okay, very simple process. Seems to be what the book's saying. It seems to be what the on-site guide is actually suggesting. That's what's written down there. That's an interpretation of it. And it's exactly the same interpretation which is suggested by the NAPIT on-site solutions book. In fact, those figures are taken from that book. Okay, so you know they have interpreted it the same way as it's written in the on-site guide and come up with the same those figures. And yeah, okay, that's arguably one way of achieving it, and it follows the guidance given in the on-site guide. But are there any issues with that? And what we've got to do is now consider that value of maximum demand and what that means to us as an electrician going to look at further works. This is a fairly small domestic installation. It's only a couple of ring circuits and a cooker, immersion, a couple of light circuits, but the maximum demand is over 76 amps, even after allowing for diversity. If we back calculate that, 76 amps works out about 17.5 kilowatts of power. So if we take that 17.5 kilowatts, even if we allow for half of that for a quarter of the day, this would work out at 52.4 kilowatt hours a day. And if we apply the average unit price, that would work out at a £227 a month electricity bill. To me, that seems excessive. Okay, so perhaps 76 amps is not actually accurate enough. Perhaps it's overestimating what the maximum demand is actually. So is there another way of doing it? Okay, so now we're on to the design guide. We've looked at the on-site guide, we've looked at NAPIT guides, we've looked at various other texts. Now we're on to the design guide. What do they say about it? Well, the one good thing about the design guide is that it goes through the process and it backs it up with a number of examples. written examples which you can follow through. So you know that you're applying it in the way that they are suggesting. It's written by the IET, the same people that write the on-site guide, same people that write the wiring regs. So if we're going to follow the wiring regs and the on-site guide, why not follow the design guide? Yeah. What does the design guide actually suggest that we do? You ain't met my wife. Yeah. Okay, so what does the design guide say? It says for the 2 lighting circuits, again, we're still allowing this strange sort of 100 watts per lamp. So 2 32 amp ring circuits, take the rated current of the protected device. For the 3 kilowatt immersion heater, we're going to take the full current load, 13 amps. So we're ignoring the cooker circuit at the moment because that is the largest circuit. Remember, that was rated at sort of like 40 amps or something. That's the largest circuit. We're ignoring that at the moment. So all the other circuits, the others, yeah, comes to 85.7 amps. Design guide continues. If you then take the cooker circuit, take the first 10 amps and 30% of the remainder. So after applying diversity for that particular piece of equipment, 25 amps, that's the largest circuit. It's the largest circuit because it was a cooker. It was rated at 40 amps to start with, yeah, or whatever it was. Yep. Take 100% of the largest circuit, and then take 40% of the remaining circuits. Well, the remaining circuits added up to 85.7. 40% of that is 34.3 amps. Add that to your 25. We've now got a maximum demand, allowing for diversity, of about 60 amps for that installation. Now, for a standard house with 2 rings, a cooker, an immersion, and a couple of lighting circuits, that to me seems much more reasonable. Remember, when we're looking at maximum demand, okay, according to the regs, it should allow for economic and reliable design. Economic, in other words, we don't want to be over-egging it, yeah, putting in a cable and a system which is capable of taking hundreds of amps when we don't need it. Yeah? But it needs to be reliable. So we can't go too far the other way. And it's getting that fine balance, that proper balance. And there's lots and lots and lots of issues that we need to consider and assess and when we're looking to try to come up with a maximum demand figure. Using the last process that we went through from the design guide, yeah, and following the information in the tables in the on-site guide, the process suggested, yeah, by the design guide to calculate the maximum demand of the installation gives us a much more reliable figure. Once we've calculated that figure, we can then enter that on our maximum demand on our certificate. Now, we've come across people filling in these certificates that when you talk to them, how have you calculated your maximum demand? And some guess, some just leave it empty. We've seen quite a few certificates where people have left that empty because they didn't know what to put in there. Okay. Some put the rating of the incoming overcurrent protected device, the actual service fuse. Okay. All of those methods are not acceptable. Yeah. When we're looking at the maximum demand, we're looking at the maximum demand of the installation as installed in the environment that's being used, okay, as being used by the people that are occupying the dwelling. Okay. And it's not to do with the service fuse, it's not to do with a guesstimation, okay, and we need to have a proper value put in there. It's important information which is required. It's also important information which is necessary if anybody should go back to do any additional works. When you go to do any ICR, it's always worth rechecking the maximum demand because you don't know what's been going on since the last time it was tested. And let's face it, not always do the people doing the installation of any additional circuits or new works, they don't always update the test sheets. Okay, should do, but it doesn't always happen. In the real world, we know it's not happening. How many times do you go to a fuse board chart and find it's inaccurate, pretty much most of the time. So suggest your process. When you're adding an additional circuit, use the information in tables A1 to calculate the maximum demand for this circuit. Refer to the EIC, providing that the maximum demand has been done properly, and not as a guesstimation, not as a service fuse, not left blank. Yeah. Look at the maximum demand of the existing installation, absorb that new circuit into that calculation to get your new maximum demand. If the installation, the supply is big enough for what the customer wants, fantastic. They can have it. And you can say, yeah, fine, we'll get it done for you. Here's your price, no problem. If the supply is not suitable, then you need to advise the customer. It's absolutely pointless advising the customer that they can have something when you know it's going to cause problems. Okay, if you set fire to their house, yeah, because you've allowed an additional supply to go in, which you've assessed shouldn't have gone in, then it's your fault. You're responsible for that. Okay. If a customer starts getting power cuts or losing the supply because the service fuse is tripping out, they're going to blame you anyway. So it's no good doing stuff because you think you're keeping the customer happy if you know when you've applied your engineering point of view that the supply is not suitable. If it isn't big enough, then the customer needs to go to their DNO. It's the customer's job to go to their DNO. They are the customer. It's their contract. You can advise them. You can even give them a letter, yeah, or dictate a letter for them, but they need to go to the DNO and arrange for a bigger supply. So if we got an example here, we got an incoming supply fuse, it's 80 amps, and we've got a 3-bedroom dwelling. It's got a cooker rated at 42 amps, well, that's the largest circuit. We've got a couple of rings. We've got a ring final for the downstairs, we've got a ring final for the upstairs, we've got a ring final for the kitchen. We've got an immersion heater which is rated at 13 amps, and we've got upstairs lights 7 pendants, downstairs lights 10 pendants. Now if we need to or want to calculate the maximum demand of this installation, okay, we've got, forget the cooker for now, we'll leave that to one side. We've got 3 ring finals, that's 32, 32 and 32, that's 96. We've got a immersion at 13 amps, okay, it's 99, 109. And then we've got the 2 lighting circuits, which is a few amps, okay? And then we need to take 40% of that and then add it to the cooker. The cooker is 42 amps. We take the first 10 amps and then we take 30% of the remaining 32. So we see how that pans out. So we're now going to allow 19.6 amps for the cooker. That's 10 amps plus 30% of 32. That totals 19.6. Add in the other bits of the circuit. Well, we've done the lights now. We've got 3 amps and 4.3 amps. Take all the other circuits and add those together. That now comes to 116.3. We take 40% of that, which is 46.5. Add back in the cooker, another 19.6. That now gives us a maximum demand of 66 amps. That's our value, and that's what we should be entering into our EIC. Make sure you're happy with that. There's a question, while you're looking at that, there's a question, what about an installation where the service head fuse is sealed, meaning unable to assess the service fuse size? Well, the direction we have is we should actually get it by inquiry. So you ring up your local DNO and say, what is the service fuse size in this installation? And the trouble is you'll quite often get somebody in the office who hasn't got the faintest clue, and they'll give you a bog standard answer. More and more nowadays, we are being given the ability to remove service fuses. Yeah, if you contact your local DNO, a lot of companies now, they will send you a pack of seals. The idea is that if you need to remove a service fuse for a change of fuse board or similar, you can remove the fuse board or remove the seal, remove the service fuse, so you can now change your fuse board. When you put the service fuse back in afterwards to reconnect your supply, you then seal it with one of these seals from the pack, which has got a number on it, and then you let the network operator know, and they will, next time they visit, it might be a meter reader or whoever, will come and put a proper seal on it. There is that arrangement. It's something that we used to do years and years and years ago. Yeah, we had all the crimps and the seals and the wires and everything then, and it's coming back. It's a bit of common sense, really. Okay, and that is happening in quite a few areas now. If you have that facility, then I would suggest that the best way to find out what your supply is to take your service fuse out and have a look inside. I'm not happy with doing things by inquiry because quite often we will be given bog standard values. Okay. Right, we'll just move on from there. David, you there?
Yes.
Can you check, because I haven't got any books with me at the moment. I haven't got any books with me at all. Can you check Jonathan's comment? No, is it? No, sorry, the one before that.
Jonathan.
Above Jonathan, before Jonathan. I can't see who
Ian.
it's from. That is it, Ian?
On-site guide, 10%
Yeah.
plus 30% of full load, not the remainder.
Can you check that? Can you check the wording of that, please, for me? I haven't got the thing with me at the moment. Okay.
All right.
Can you check that for me?
Okay.
While I just sort of push on the next couple.
That's the on-site guide.
It's in the on-site guide wording.
My favourite book. Yeah, I'll have a look.
If you could, yeah. All right. Yeah. Okay, so we've got a maximum demand of 66 amps. Okay. If we then consider the customer might want an extension built, okay, so they require a socket out and surround the extension plus a 7.5 kilowatt electric shower because they like tepid showers. Yeah. The previous other loading was 116 amps. The new ring circuit is 32. The new shower is 32.6. Add those on, we've got 180.9. Take 40% of that, we're at 72 amps. Add the cooker back in, we're now at 92 amps. If the service fuse was 80 amps, we can't allow that new installation. Okay, we've readjusted, we've absorbed the new circuits into the maximum demand calculation. Okay, and we've now exceeded the rating of the service fuse. So we're up to 92 amps. Can't be done. However, reconsider, and this is the strange thing about maximum demand, rather than putting a new ring final circuit in, you extend the downstairs ring. So the only additional load you have to consider now is the shower. So previous underloading 116 amps, the new shower 32.6 brings us up to 149 amps. 40% of that is about 60 amps. Add in the cooker, we're back up to 79 amps now. We're now within the 80 amp service fuse loading. All right. Consider also the fact that obviously the lighting, we've added about 7 amps for lighting, 40% of that anyway. Remember that it's unlikely we're going to be using 100 watt lamps and lights. Quite commonly going to be using LEDs, so we're going to be saving maybe a couple of amps there anyway. So the way we install things, crazily enough, affects the maximum demand values. And this is, again, something you have to take an engineering view on and think, well, is that really the case? If I install it as an extension to the existing ring, it's okay. If I install a new ring, it takes it over the maximum demand, but they're going to have the same amount of equipment, So again, it's one of these things where you may take an engineering view on that. And this is the thing about all these bits of guidance, is they are there purely for guidance. They are not set in stone. All right, and we have to apply these the best way that we can.
Okay, I've found it, and some of the guys have pointed this out. Okay, so table A1, which is also demand of appliances, says to the cooker it's the first 10%, and then it's the 30% of the wording is of the remainder of the rated current.
Yeah.
Okay, so for the A1, which is a demand table, it's 10% plus 30% of the remainder rated current.
Yeah.
Table A2, which is the diversity part for the domestic, it's worded 10% plus 30% of full load of connected cooking appliances.
Yeah.
So that's not confusing, is it?
Well, this is the trouble, isn't it? You've got different tables there, and one says the remainder of the load, one says 30% of the full load. And this is the trouble with the on-site guide and the application of the on-site guide. That's why I don't really tend to stick to that too much. I've gone by what it says in the design guide, and I followed the examples that are laid out in the design guide. And the examples in the design guide take the first 10 amps and then 30% of the remainder. And they are worked examples, and they're laid out, and they show you how to apply it. And
I agree.
This is why the on-site guide to me is always a frustrating book, because it gives you a certain amount of information, doesn't tell you the full story.
Yeah.
It's like having Harry Potter, the first two, and then you don't read the rest. You think, well, what the bloody hell what happened?
I agree more with what Peter said earlier on. He thinks the section needs a complete rewrite. He said,
absolutely, yeah.
It's too formulaic, which is a word for the day for me. I agree. I mean, this is written mainly back when we had just resistive loads, and the utilization of systems was different. It needs to evolve. It needs to change. And he says there might be better examples were provided, and data sheets, industrial design, demand per square meter. I mean, if you look at energy efficiency, that's where that's going with the Barrow-Mead Center method and all that stuff. I'll let you carry on.
Yeah, no, I totally agree with you. This is the big issue with the on-site guide. Why don't they have worked examples in there? Because worked examples actually lay out and explain things better than two tables, especially if the two tables tell you to do two different things with the same appliance. And the wording is different, so the interpretation is different. It's nonsense, and it's a real issue. And this is one of the things we have as a recurring theme all the way through the regs, isn't it? Interpretation, and it is crazy. That's why, as I say, I've gone by what the design guide has said, and I've followed that. They've got the laid out examples, and I can follow those, and I can see how they've treated each of the calculations and what they've done with it. So just to finish off, we're sort of about 50 minutes-ish. Yeah, well, it's close. Another thing to consider before we move off of this is these things are coming in more and more and more now. Electric vehicle charging. The customer asks for electric vehicle charging point, or maybe two, because they might both have an electric vehicle. You've got 2-car families, 3-car families. Depending on the mode of charging, these can add a considerable amount to the maximum demand. And the other thing to consider, obviously, is that the time when most of these things are going to be plugged in is when they come home in the evening. They plug into the car charging point, and then they go indoors and they put the oven on, the kettle on, the shower on, and so we suddenly get this huge increase in current. With some of these car chargers, depending on whether they're doing trickle charge, whether they're doing fast charge, we're looking at, in some cases, 22 kilowatts. Yeah, that's for one car. Okay, so the mode of charging needs to be considered. And when we're looking at electric vehicle charging and putting these in, we really, really, really do need to look at the maximum demand and diversity, because there is going to be quite a few installations out there that are not going to cope with electric vehicle charging. Remember that a lot of people are being told they can charge cars off a 13-amp socket. Well, yeah, you can. It's like, in fact, you can hammer nails in with a pair of pliers, but yeah, it's not something you'd do by choice. Okay, so be wary of anybody. When you're looking at electric vehicle charging, you need to look at the whole installation and assess the maximum demand. So to summarize, maximum demand requires experience and knowledge to be applied for successful calculation. There are different aspects of the installation, the mode it's being used in, and a number of people. Okay, lots of things will have a significant bearing on the allowance that we can make for diversity. There are various books and guides that tackle it in different ways. Sometimes in the same book, it tackles it in different ways, as we've just seen from the on-site guide. You've got to use your own skill and judgment there as to how you apply it. Remember, it's for reliable and economical design. So we don't want to go too mad, put in huge cables and huge distribution boards and cost a fortune, but at the same time, we mustn't underestimate it, okay, because that can cause fires, it can cause interruptions to power, it can cause all sorts of problems. So it's getting it right. Follow the guidance that is given, the guidance that you are most happy with. For me, as I say, I use the design guide. It lays it out, it explains it, it gives you worked examples. And that's what we need. That's what we need. We need guidance, we need direction from people like the IET to give us the correct information in a concise format that we understand. Okay, any other questions there, David?
Okay.
Richard said about the 22 kilowatt 3-phase. They probably are, Richard. They probably are. But if you've got two cars to charge at 22 kilowatt, you're looking at about 7 kilowatt per car per phase. So you could have two cars. You could have 14 kilowatt load, which is 60 amps.
Yeah, it's I mean, somebody can pull 90 amps if you're the one, these Tesla banks and stuff for the services, because you want to charge whilst you're having your crap, basically. And it's going to be a huge demand, but it's obviously more suitable in the domestic market for one. Add them together, and bear in mind that they are looking at things like vehicle to grid. So we'll be looking at obviously, charging overnight, and then obviously you go to work, then you come home, you've still got some power offering that back, and then charging again overnight. So it is moving around. Okay.
I've put that in there because obviously with the business of, as we change over the next God knows how many years to electric vehicles, at the moment a lot of houses or a lot of families have 2, maybe 3 vehicles. You imagine you got 3 vehicles to charge. Okay, it could make a considerable drain on your electrical supply, and it's coming. We're not going to avoid electric vehicles, so we need to consider that when we're looking at maximum demand.
Yeah, I'm actually just getting some information now from Matthew, the guy from Matty, and he's giving some information on the electrodes and stuff. I might actually see if we can get him onto a webinar or something, just to help talk about electric vehicle. Okay, questions. Using the worked example, we're applying diversity to the largest appliance, i.e. the cooker. Is that a question, or is diversity applied to the system altogether? One question from Peter. Using the worked example, we are applying diversity to the largest appliance, i.e. the cooker. Yeah. I mean, cookers are the common example, because the thing about the cooker, I mean, there's another question from Ian. What about instantaneous water heaters? That's just, one purged larger demand. So we need to really understand the behaviors of the equipment. I mean, you had that slide that showed like a washing machine, understanding the different characteristics compared to a tumble dryer, which is a constant demand. Demand behavior, equipment demand behavior is important.
Yeah, all these things need to be considered.
If you have water heaters that are thermostatically controlled, and you put 3 or 4 of those on the supply, but then you put 3 or 4 instantaneous, which of those is going to draw more demand? It depends on obviously the use. Depends on the demand. Depends on the utilization.
Yeah, what is quite confusing quite often is the fact that even in an installation, maybe with an electric cooker and an electric shower, the electric shower could be 10 kilowatt. Yeah, so obviously that is going to be instantaneous heating. It's going to be pulling that 10 kilowatt all the time that shower's on.
For how long?
Even so, when you come to doing maximum demand and diversity, they talk about the cooker being the largest circuit, even though you end up taking 10 amps and then 30% of the remainder or whatever. Yeah, so when you look at the actual current demand, it actually can work out when you're doing your calculations as less on paper than the shower current demand. But we still use the cooker as the largest circuit, and that's because the overall rating of the cooker is actually larger than the overall rating of the shower. Yeah. Before any diversity is applied. Yeah. And this again is a confusing issue. So again, having worked examples like in the design guide helps to cut through all the fog.
Okay, here's one from Chris. How would you consider the loading on off-peak heating, given that now typical households may utilize this cheaper rate to run expensive appliances, or as we said, car chargers? So when we look at demand, do we have to start considering a off-peak demand?
This comes back to, again, something that we've picked up a couple of times on some of these webinars, is that you really have got to talk to the customer. You really have got to speak to the customer, get as much information out of them. How are you using this installation? When do you put your heating on? When do you put your washing machine on? You know, when do you do this? When do you charge your cars? And we need to know all that information. We can't just guess this stuff anymore. We need to get proper information from the customer. And you could even make a small report up. You know, you go and see the customer, they want some work done or whatever, you go and do a rewire, whatever it is, and you could just go and see the customer and just a short interview. How do you use this installation? How is this installation utilized? When is your maximum demand? What equipment do you put on when? And this now is becoming an important facet of our sort of installation process, because without that information of how it's going to be used, how the hell can we put an effective installation in if we don't know how the customer's going to use it?
Again, I every time I say the word utilization, that's exactly what I mean. You know, observing the customer and asking them for their operational behaviours. Otherwise, we are going to potentially, if we make assumptions, we're going to balls it up. We're going to balls it up completely. Yeah. So Ian said, "What if the largest circuit is an instantaneous water heater? We'd have to."
Well, again, this is one of those things. I
think there's no diversity allowable for that, isn't there?
No, but then
according to the table,
you know, it's only on for however many minutes you're in the shower, and this is one of the things that you could end up overestimating what the maximum demand is because of that. Yeah, so that most of the time the actual installation is running well under that. And this is one of the annoying things. You've got to make that engineering view. Ian says about getting a government grant to get bolder books. Yeah, I wish. Might be you could have a go now at the moment. You might be able to get it under the current sort of regime. But
another one from Ian. What if the domestic supply is already 100 amp and our calculation shows it's inadequate?
Again, this comes back to what do we do about things. If you do a maximum demand calculation and you feel that the maximum demand is being exceeded, it's exceeding the actual load, look at the time current curves, because remember that fuses will accept a sort of a certain amount of overload for a period of time. Look at the size of the cables, and you have to then assess it. But the minimum you would do is do a risk assessment and a report to the customer and say, by my calculations, you've exceeded your maximum demand, and we highly recommend that the following actions are taken, i.e., talk to the DNO.
This takes me back to the example. This takes me back to the example of what he had in Bracknell. I mean, he's added to the question here that the DNO quoted 18,000 for an upgrade to the supply. So immediately, it's economically, you want to try and find a more suitable solution. And we had the situation in Bracknell where the lady was having her kitchen done, and she had the hob, which was on a 13-amp plug, and she went to B&Q, and there was another hob there that had the same chrome effect to the fridge that she'd got, and so she wanted to swap it, and the expert in B&Q said, yeah, that's fine, I'll go straight in. But it was a 10-kilowatt induction hob. We had to tear some of the ceiling down, because there was a laminate ceiling above. We did keyhole surgery, and we got the new cable there. But then she had an electric shower on, she had the electric cooker, she had the electric hob, and the demand was exceeded. And so we just talked to her about the use of the system. And she actually, at that point, she said, well, I'll have the hob on when the cooker's on. Now, the shower, she didn't think about it, but she had a number of kids, and she had like 4 daughters or something. And I said, well, it's probably going to be fine. But she decided there and then just to have the shower converted for hot water instead of electric. So, a bit of discussion with the client was enough. And she, if they're aware, then they know. I mean, the overcurrent device is going to do its job. If it pops, it pops. But if they are aware of that, then they're aware of how they're using the system. That's the key there.
Ian's mentioned there about it being risky to base your maximum demand partly on the occupancy profile. Old people have got a habit of dying. and larger families move in. Absolutely, yeah. And this again opens up a whole can of worms. We're bringing in now the idea of the fact that
the problem
from our point of view, whenever there's a change of occupancy,
Mm.
there should be an inspection and test take place. And that's something we've been banging on about for donkey's years. If you have a change of occupancy in a dwelling, it could be change of ownership, it could be rented or whatever. Whenever there's a change of occupancy, there should be an inspection and test take place. And then the maximum demand could be checked at that point. Who's moving in? Okay, well, it's a family of 12. Right, okay, we need to think about how that's going to be utilised and whether or not that's going to affect the maximum demand rating.
Yeah.
So this brings in, it starts to open up other sorts of avenues of discussion. And this is something we've been on about for ages, isn't it? About there's a change, there should be a test.
The problem is obviously how, the example we showed earlier on with the houses, the different quantity of persons, that's from the design guide, and it's because obviously when you supply a street, they have to assume that kind of dynamic. But we've seen this before. When I worked with a local authority, there were these communities of people that didn't work for much, and they'd all just be at home all the time, and they were always pulling power. So the diversity, the idea of that is, again, you have people who go to work, so they take off the demand, and then you have people who may stay at home, and they kind of balance. But we had a couple of feeder pillars where the fuses were always popping. And we then looked at what the problem was, and obviously the housing department had basically kind of, over a couple of years, about 5 years or so, had just started relocating some of these families into one little corner of this cul-de-sac, just to kind of like make other people happy. But they were popping all the feeder pillars it was basically like a party every day.
I had a situation last summer where I was at the sports place that we work at occasionally. Yeah. One of their residential properties, the person living there had reported a socket melting, and it had been replaced by their own electrician. It had then melted again, and it had been replaced again. And I was asked to go over to look at it, and called me and said, "Can you go and do a report on it?" I said, "What's it doing?" They said, "It's feeding it was a hot tub." And I went over, and it was plugged into a 13-amp socket, a hot tub. It was a plug-in RCD plugged into a 13-amp socket. And I was just sort of, I don't think a hot tub can run off 13 amps. I've never seen one running off of 13 amps. And I said to the guy that lived there, I said, "Look, my initial reaction is there is no way at all you can run that hot tub off of 13 amps."
What was it pulling? Was it like a...
do you know what? I didn't actually have my ammeter on me.
Because the Lazy Spa ones come on a 13 amp plug.
Yeah. Well, I said to the guy, I said, "I'm not really sure that this could be running off of 13 amps. So I said, "Have you got the specification?" He didn't have the specification. I said, "Well, what makes you think it runs off 13 amps? He said, "Well, the sales guy told me it would." Okay, fine. I said, "Well, I don't think it can. I think it's pulling too much current for 13 amps, not as a constant load." I said, "And this is why it's melting." He said, "Well, no, I was told it could run off 13. He would rather believe the sales guy than believe me, even though it actually already melted 2 sockets. Well, and then I said to him, I said, "Well, but my reasoning is," I said, "I think this is too much." And I actually unplugged the RCD. It was red hot. When I looked, it had melted. I said, "Well, it's melted again." I said, "And you're still adamant that it'll actually run off of 3 kilowatts?" He said, "Well, yeah, that's what the sales bloke said." So this is the thing, they don't listen to us. They listen to the sales guy that's selling them the stuff. And this is the same with car charging. Well, I've had people say that, well, we've been told we can charge this off a 13 amp plug, and they go and plug it in, and then it melts, it catches fire, and they wonder why.
I mean, they've introduced regulation to allow for the granny cable to go for trickle charging, but that's not the behaviour that the salespeople actually suggest. They suggest just plugging it in. What if the largest appliance is a 9 kilowatt shower?
Well, you use that as, if that's your largest appliance, it's your largest appliance, isn't it? You can only follow the guidance, okay? But as again, it's guidance, so you use your engineering view.
Take for example,
as to how it's going to affect things.
Yeah, I mean, again, if you remember a couple of years ago, or maybe just long ago, the 2396 design project was a training center.
Yeah.
Yeah. And every single trading bay had to have a 16 amp socket.
Mm-hmm.
And the point of that socket was obviously a control socket, a bit like actually the one I've got up there.
Yep.
Up there. That is a 16 amp socket. And the reason that's a 16 amp socket in my home is because there's no RCD protecting that. So I can plug all sorts of randomness in there and actually test RCDs here instead of tripping there.
Mm-hmm.
And so the same thing. Now, obviously, it's properly fed, but when you actually do design and demand calculations for that, you don't add 16 plus 16 plus 16 plus 16 plus 16 because you understand the use of the system.
Yep.
And it's the same principle what we need to do with this. And this is why we do have to speak to the customer, but we have to have some kind of template, as it's been suggested. People die, people move out, people move in. So it's finding that balance. It is finding that balance.
There should really be a risk. There should be a maximum demand risk assessment. There should be a guidance form. Yeah, just so we can actually sit down and write a report up and look at things like, what sort of equipment is there, how many occupants there are, how they're using it, the dynamics of the use. Do they all come home at the same time? All sorts of things that can affect what the maximum demand will be at any one time. And we need to perhaps just do that as a report.
Yeah.
Rather than just have a little box on our sheet that says maximum demand, and we put a figure in there. But that doesn't tell us is how we arrived at that decision. Yeah.
And again, I mean, as Peter's probably there's the guidance is there's too much formula, and there's too much play with it instead of it just instead of just having a good understanding on use of the system. It's like when we add up all the MCBs and we go, 40%. I mean, some MCBs. I mean, again, I spoke to Paul recently. Paul Meehan with his railway. He's reading the data he's getting back from Schneider, and he'll say about something like 40% of his circuits are doing nothing most of the time. The data comes back to says they're doing nothing, and he can actually restructure the system and lose a lot of cabling.
Yeah.
Because of the way it's used. And that's the thing about maximum demand. If we had user data, we can then adjust for that.
This is the bottom line. The summary of it all really is the fact that we need to treat every installation on its own merits, and we need to gain loads and loads of information, not just of the equipment that's there and the circuits that are there, what's actually in the fuse board, but we need to talk to the customer.
At the end of the day, there's a need for some kind of template for the domestic sector because, again, people will move out, move in, and they won't necessarily have the right checks carried out. But obviously in the workplace, we do have a need for employers to provide a suitable fixed electrical installation, the need for maintenance under Electricity Work Regulation 4.2. So it's much more suitable in that kind of environment for us to be a lot more precise in our design. But obviously, in the domestic, there probably is a tolerance for us to be a little bit more generalized in our assumptions of the behavior, as long as we don't cock it up, basically.
It's striking that happy balance.
Yeah.
You don't want to underestimate, you don't want to overestimate, and this is the thing. So whatever you do, I keep coming back to this. It'd be great if we could actually do a little written report on how we arrived at the figures we arrived at, rather than just sticking a number in that box, which has got no other information about it. What's your maximum demand? Well, it's that. Bang. How did you arrive at that? Just took a figure out of the air.
Well, the device. I mean, when you look at the diversity tables, the way you take a certain percentage of lighting, depending on if you're in a hotel or a shop, it makes you understand the use of that. And so, adding the lighting demand and then taking a percentage in regards to its use does make some form of sense. But in the domestic, when we have all of the circuits and we then take a percentage, that's just where we just don't understand it because it makes little to no sense from one home to the next. But let's go through these questions. Okay, Chris says, would you go as far as switching on all the loads and using a clamp meter to get the measured load rather than a calculator? The problem with that is it's simulation. Turn everything on. It's not really representative of the normal use. But it is a method to see the demand. So if you wanted to know the potential maximum capacity, fine, but that might not be representative.
But then again, they could bring stuff in. They could bring new appliances in, and this is one of the issues with domestic, of course, is the fact we've got no control at all over how the people are using it. Quite often, in industrial commercial, you've got more control because the bosses will say, "Well, you don't bring stuff in." Yeah, they will actually provide the electrical equipment, so they've got control and they can manage that much better. In a domestic environment, you don't know what they're bringing in. They bring in, as I say, an inflatable hot tub. They bring home electric barbecues, and they plug these things in. And that's again, this is why you talk to the customer. Don't just go around and see what you can see. You don't know what they've got stuck in the garage that they bring out at certain times of the day.
Also, if you're doing it as a investigation, do be careful, because one time at this sports place we keep mentioning, there was can you remember that there was a cleaner company that hired out a flat? Remember down the bottom.
God, yeah.
There was they had the power kept tripping. Cleaner company were basically renting a flat. They had a contract on the site, and their power kept tripping out. And we got the radio, and I got called up, and I put my mega clamp meter. I went down to this 3-phase board, and there was this cable. It looked a bit brown, but I thought I'd check that. And so I put the clamp meter around, and I rested it on there, and I left it for about 20 minutes. And then it was pulling about 98 amps or something on it must have been either a 45 or a 63 amp supply. But then when I lifted it back up, it was stuck, and the actual heat from the cable had melted the jaw. It had melted the actual cloak. I've got it here somewhere. It's got this little thing, and it broke it. But they had a board. It was all 3036s. And it was cold, so they were plugging convector heaters into all the sockets. And the 3036s were doing nothing. It was a Merlin-Gerrin board, and that overload kept going. So do be careful if you can use a clamp meter to check demand in a fault finding scenario, because you might break a tester like I do. Do car chargers incorporate priority switching devices? This is obviously some of the earlier ones did not, but what they're trying to do is obviously create these chargers now that are quite smart, and they'll start. I mean, in a few generations' time of these testers, they're going to start talking to our boards, and they're going to, especially with back to grid. But yes, the principle is obviously the car will monitor the current that you're pulling, and then there's some. I don't know sure where the device goes, but it goes into the board, or it assesses the demand on the rest of your system. And if you pull a large demand, it will then take its demand down to protect and not over assume the demand of your system. They basically want to pull as much as they can when they can,
which is great.
And then when you pull more, they'll let some go,
which is great. But it needs setting up in the first place, doesn't it?
Yeah.
So obviously you need to make do that setup so you know how much the maximum demand is, what the available supply is.
I don't know. Does the Zappy do that? I can't remember now. One of them did it.
Well, I mean, otherwise, if you've got a supply of 200 amps per phase coming in, a 3-phase installation, and you've got a supply of 60 amps in a little old sort of terrace cottage, and you put the same charger in, you don't want it behaving the same way, do you? It's got to react differently to.
So you've got to tell it.
It's got to be set to whatever load is allowed.
Yeah,
surely.
Yeah. Most hot tubs need 16 amp supplies. Yeah. Obviously the fixed ones, probably yours does, doesn't it?
Yeah, mine pulls about up to 25 amps at certain times. Yeah.
Wow. Yeah, I'm too poor for that. I've got a puddle. I threw water in a puddle.
Yeah. Right.
Yeah. Do you think 3-phase will become the norm in future domestic installations because of the increased demand, car charging, electric water heating, etc.? Well, the infrastructure isn't there for that. And have you checked out, Reese? Have you checked out the E5 podcast? Was it podcast video I did with Paul on the future? And actually, we uploaded just yesterday on my YouTube channel, SparkyNinja YouTube channel, a webinar that we did on the future of BS7601. At the back end of that, we talk about 60364-8-1, 2, and 3 energy efficiency, and they're going down this direction of prosumer. And the point of prosumer is we're going to start converting our installations so that we produce power, we store power, and we consume power. So we produce and consume. Prosume. We're obviously trying to dampen down our demands on the grid, because the grid is well under equipped for that. I had a meeting I have these regular meetings with John Ward and Paul, and we were looking at this data about the amount of losses from the network of the power that's generated, the amount of it that's losses. My jaw hit the floor. The amount of stuff, it's more than half is lost just with AC generation and transmission. It's lost. If we can generate in DC and we can store in DC with battery systems, which is being looked at into Section 557 in the future, then we can use them straight away. So the intent is for our systems to evolve. The Foundation Earth electrode, you maybe remember that from the draft of the 80th edition. We've just been talking about electrodes. We're talking about not doing electrodes because technology is smart enough not to need electrodes. But then Foundation electrodes will come in anyway. So
I think if anything, we're going to start using less, aren't we? Because from the grid anyway. Because
we're going to use less.
Because this business of being a prosumer rather than a consumer, and various other things, we're going to end up actually
there's two things
demanding less.
Yeah, we're going to use less, obviously, lighting, power, efficiency, utilization. But there are two things: there's electric vehicles, and there's obviously the removal of gas boilers. Somebody on a previous webinar mentioned that there's they sent some links. I think it was Daniel about hydrogen. Is it hydrogen being used?
Yes.
Yeah. Boilers. They're trying to find new technologies because we can't just put everything on the electrical demand. The infrastructure isn't capable for that. Immediately, yes, three-phase would help lower the balance and put the power demand on. But the question would really be as to as homeowners, etc., why we need that demand with the way we use electricity. And I should imagine bigger questions would be raised on that first. Electric vehicles are, one of the exceptions because they're trying to force our hand on that. But again, they want us to power the vehicles as much as we can from our own generated source of energy. So we'll be looking like new homes in the next 10 years or so. Every new home will have to have solar, ground solar, and maybe wind, two of those three sources, and they'll have to be storing that energy instead of exporting it. Yeah, so. If an installation has a generating set, say 4 kilowatt solar storage facility, say Tesla Power Wall, how does it affect the number we put down? This is where obviously we're going to need to evolve the way it works, because right now there's a document that's available in January. MCS have updated a document that refers to other standards about storing energy. Because right now we're going to need some, like we had with PV, we had obviously, what were those standards? G89, or what was the other one? I can't remember. So many standards in my head right now. There are other standards that we have to refer to, and then there's the MCS standard that kind of amalgamates all of those. It's in its infancy right now, or it's in its very early execution. I'll do some digging and see if I can find more precise information on that one for you, Tom, because that's an interesting question as to how we would deviate our demands. With our demands would be, how would you deviate how much of the maximum demand is, consumed instead of produced later on? What fun!
Indeed. Yeah, lots to consider.
What fun! All right, that's the last question. Anything in the chat pop? You got the chat open?
No, Peter's had to go because he's a lesson to deliver. Scott's mentioned a BBC documentary on the grid that was on a few years ago, which was good, but it was saying that they were under-equipped then. This was a couple of years ago, so yeah.
Cool. I think I'll do something with Pete because he's teaching and stuff. It'd be nice to get him to kind of we can just do some stuff. All right, okay, guys. What time is it?
It's about 25 past 3.
Yeah, all right, over the hour. Okay. All right, guys. Thanks for coming into this webinar. What's the next one? It's tomorrow morning.
Tomorrow morning, there's one on something or other.
Fire.
Might well be.
I think so.
Yeah, I think so. Yes.
We are experts.
And then we've got one on
cable calcs too.
Cable calcs and stuff. Yeah.
Yeah. Okay, so we're going to do a webinar. Next webinar from us is tomorrow morning at 11. It's Fire. This, again, is a webinar we've already delivered once, but it had a lot of great discussion. And Mr. Watts here with me is going to join and talk from his perspective of a former firefighter. I've had a couple of other people who are also firefighters who've had a good input. So I'm going to do a tweet and an Instagram and see if they want to come in and offer some input themselves. One of them reminded me, and it's in the presentation I put on YouTube, about that little harness thingy that you put behind the tank and the helmet. The little thing that they've got. I've got that on the slide I put on YouTube 2 years ago. So I'll add that to the presentation for tomorrow because he reminded me of that. I've waffled. Cheers, guys. Thanks for cheers, Tom. Thanks, Chris, Ben, Paul, everybody else. Enjoy the rest of your day. It's a lovely day here.
Indeed. Let's get out in the sunshine. Get some vitamin D.
Crack one open, vitamin D. And if there's a list of chores for you, pretend you've got homework. Yeah. All right.